Movement in nature has always inspired Kia, and now it has inspired a completely new musical instrument. Introducing the Kia Instrument, the world's first instrument that's scientifically designed to inspire you. A collaboration between the House Audio, renowned synth builder Arthur Joly, and Kia, built using the sounds of movement from nature to make music that puts you into a creative state of flow. Discover the inspirational sound of the Kia Instrument at kia.com.
Kia, movement that inspires.
This is Scientific American's 60-Second Science. I'm Ashley Patt. You might say that Guillermo Pons is a scientific monster hunter, even though he thinks that term, monster, never really captured his subjects right.
So they are regular animals that have gone through different developmental processes that would end up building a body that is not what you expect.
What this researcher based in Madrid, Spain actually loves is the oddly amazing animals. After all, he studies two-headed worms.
We have these worms that are usually regular worms, like with one head and one tail, and that's normal, but sometimes they may have two heads or two tails. And on the other side, there are worms which have one head and many tails always.
Officially, he looks at bifurcated annelids, meaning things like earthworms that have come out of their larval stage with two heads, or spontaneously sprouted two tails, or some other combination of mixed up appendages. We know that certain species, like some salamanders and insects, have the ability to regrow appendages in a time of need. But there's this one phylum of worms, the annelids, that can regrow unlike anything else that we've ever seen in the kingdom. Their segmented bodies, like an earthworm with rows of ringed compartments, help them easily regrow a new head or tail at the first sign of trouble. Or even crazier, they can regrow an entirely new right side of their body if sliced in half.
Worms that do these crazy things that are very weird, very strange things that these worms should not, quote unquote, should not do.
Once Pons started studying the anatomically death-defying lengths to which these worms would go to grow and survive, he was totally pulled in. And he realized that he and his team weren't the first to be fascinated. Pons found that there was a golden age of research on monster creatures during the 18th and 19th centuries.
100-plus-year-old literature would refer to these animals as monstrous creatures or monsters or oddities, or there are all these variations that describe them, and in the end these animals are not monsters.
A fixation with the reanimated monster makes sense, especially back then. Author Mary Shelley's novel Frankenstein was published in 1818, and it only further intensified interest, and some of that interest translated into actual research. Pons and a team of international researchers conducted a wide-sweeping review of the existing knowledge about monster worms. They dove into 275 years' worth of research, combing through scientists' observational journals, reading historical texts, and even reaching out to the broader scientific community to see if anyone knew anything about records of abnormal worms. They wanted to understand all of the different types and patterns of bifurcation and see if there were any clues about how the oddities developed. Their search landed them in a jackpot of both history and science. They came across documents and drawings of bifurcated worms from around the world, in Latin, French, and German, all the way to Russian, Japanese, and even Indonesian. All in all, they spent over a year working through the archives, translating old texts, and following the trail of monster worm clues. What they learned is that bifurcation in worms has been observed in over 60 species of worms across the annelid family tree. And in some species, up to 20% of the juveniles ended up with some form of bifurcation. This work was recently published in the journal Biological Reviews.
And that means, for example, in the case of bifurcation, that when an animal is cut and is regenerating, for example, the tail, there then needs to be some mechanism that specifies where this tail is going to be, how is it's going to be oriented, what is posterior, what is anterior, what is left, what is right, what is dorsal, what is ventral. And these mechanisms can be disturbed, and this might lead to different anatomies. And that gives us clues about what is important during this process. Of course, these are the baby steps, so we are just pointing towards this process, this phenomenon. We are saying, okay, hello, this happens. There are these animals that are doing these weird things. We should not forget about them. Let's look into them.
They also realize that there's a strong correlation between the type of bifurcation and the internal organ development, meaning the way that the worms were split reliably indicated if extra sets of organs were present. With this type of intel, Pons and his team were able to essentially draw up a blueprint or how-to guide for reliably and repeatedly creating bifurcated worms, which is potentially a very useful resource for scientists interested in studying the mechanisms of development. This long-forgotten study of worm developmental anomalies seems poised for a comeback. According to Pons, this information could extend far beyond the annelid and even insect worlds to help us better understand how things like growth and development actually happen, in both the normal and the monster ways.
In a sense, we are now following this trend that they started then, studying these animals to try to understand bigger pictures in nature. Usually development leads to a certain way, to a certain point. So you have a development that ends up in an anatomy that's more or less conserved, but sometimes it doesn't. And that can teach us something about developmental processes, and that's interesting.
Thanks for listening. For Scientific American's 60 Second Science, I'm Ashley Papp.